Okay, solutions to the core section of the 2020 trial exam 2 for Heffernan. Okay, in the first question, it says the water quality of a river is affected by a number of factors, including pH level of the water. pH ranges from 0 to 14. The stem and leaf plot below shows the pH of 24 rivers. So I'm just noting that there's 24 numbers there. And now it says write down the modal pH of these rivers. So I'm looking for the most common one, and I can see that, sorry, this is the stem. It hasn't transferred well onto the iPad, but anyway. And you can see we've got a lot of 7.3s, and we've got to be careful when we look at the key that they're actually, it means 7.3. So we needed the pH, the modal is 7.3. Okay, a healthy river is typically has a pH between 6.5 and 8.0. What is the percentage of these rivers that satisfy the requirement? So what I want to see when we see percentage is you write the rule for percentage. Percentage equals the amount over the total times 100. And we saw before that the total, there was 24 numbers, so that's where that number came in. Now, the amount that's satisfied, so the ones that are between 6.5 and 8.0, so I've highlighted there, so I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I have 18 out of 24, and I times that by 100, and I end up with the answer of 75%. Okay, use this information in the stem and leaf plot to complete the table. So they wanted you to get, you needed obviously to get the median. So you could type all the lists in, which is what I've done down here, and look for the median, and found that it is 7.2. So there's one way to find it. So 7.2 equals the median. Another way could be that you go to the position. So if you go n plus 1 divided by 2 will give me the position of the median. So we know that that was 24 plus, n was 24, so 24 plus 1 divided by 2. So it's at the 12.5 spot. So if I just counted through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and 13, so you can see that the 12th value was 71, and that was the 12th, and the 13th value was 73, so the halfway, sorry, 7.3, so the halfway mark between there is 7.2. So that's just another way of showing the median, or calculating the median. You have to decide which one's quicker. You might look at other questions further ahead. Is it going to be worth putting the list in, because you need other things anyway? All right, now it says show that the river pH 5.3 is not an outlier. So once again, we need to note that it's not an outlier. We need the Q1 and Q3. So this is hopefully in reading time. You've seen that, and you know now, yeah, it is going to be worth putting this in as a list to find the median, because you need the Q1 and the Q7. So if you look at 5.3, that's going to be a lower outlier. So I'm going to use the lower formula, which is Q1 minus 1.5 times the interquartile range, which equals Q1, which is 6.7 minus 1.5 times 8.5 minus 6.7. Well, actually, they gave us the Q1 and Q3, so we didn't even need to work that out essentially as well. So maybe back there, you don't need to put the list in. You've just got to decide. Try not to be too indecisive, because you'll end up wasting time. So just have a strategy you're going to use and do it. Sorry, this is 7.7 I've read the maximum there. So Q3 is 7.7. So when we work out that calculation, it's 5.2. So you then have to write a little statement. So you have to show this, and then you write, therefore, 5.2 is less than 5.3. And so 5.3 and is not an outlier, or is larger. Okay, so 5.3 is larger than 5.2, so it's not an outlier. Just you need to have a little statement there. You don't have to use the symbols, but you do need a statement. Okay, the water quality of a river is also affected by the concentration of phosphorus in the water. The box plot below shows the concentration of phosphorus in milligrams per litre for 35 rivers which were tested between 2010 and 2017. For these two variables, year and concentration of phosphorus, how many are numerical variables? So there's only one numerical variable, and that is the phosphorus. Okay, so how many of the two, how many are numerical variables? Just one. Okay, so this one is numerical and it's measured, so it's probably, we could say, is continuous. And this variable year is like a categorical, because it's a label, but because we know 2010 comes before 2017, we'd say that's ordinal. Okay, it says write down the distribution of concentration in for the distribution of concentration of phosphorus in 2017, write the range. So range is maximum minus minimum. So you look up on your graph, and we want for 2017. So my maximum is here, which is 0.2023. And remember, an outlier is still your minimum value. It's minimum or maximum. So in this case, it was minimum. So go down there, and that's 0.0 minus 0.03. So we end up with 0.2 is the range. Okay, and describe the shape of the distribution. Now this is for this 2017. Now you've got a big square at the start and then a small square, so that one is negatively skewed, with an outlier. So you need to comment whether there is or isn't outliers, so just make sure, so it's negative skewed with an outlier. Okay, for the distribution of concentration in 2010, explain why the mean and the median would be appropriate measures of centre. They're only appropriate together if the data distribution is symmetric. So because the distribution is symmetric, both the mean and median are appropriate. And we probably should say without outliers, because an outlier would affect the mean. So it's symmetric shape without outliers, so that's why it's appropriate. Okay, using the information from the box plots, explain why the concentration of phosphorus is associated with the year in the rivers were tested. Give appropriate statistic answers in your answer. So because it's just 1 mark, you probably only have to use one statistical thing. And I often think that using the median is the easiest way. So we'll do that. Okay, so I'm going to say that the median increased with the year. So I said the parallel box plot shows that the concentration of phosphorus and the year in which the rivers were tested are associated because the concentration increased from a median of 0.1 milligrams per litre in 2010 to a median of 0.2 milligrams in 2017. Now, you could write this statement all the way up to here because, and you could say because the shape of the distribution changes from negative, from being symmetric and going to negative skewed. So that is still a fact that you're showing. Because it's only 1 mark, we just have to show one thing, so you could have done that. You might also refer to, say, the IQRs, because this interquartile range is smaller and then it increases to a larger IQR. So that's when you measure the IQR, it's the distance of this box. So you can see that changes as well. So you could have used that fact, and then you just change that bit down here to whatever statistical fact you have. So if you had to explain 2, there's another one, there's another few things you could write. Okay, question 3. Salinity is a measure of the salt that is present in water. Salinity in milligrams per litre of a rivers were tested on 20 occasions and recorded against the amount of rainfall for the previous 24-hour period. So a least squares regression line is fitted to predict the salinity of the river. So you can see that predict often means the y, means the y, and you can see that, or the response variable. So we can see that there, and the rainfall during the previous 24-hour period. So they've given you a formula here. So this is the least squares regression line of that least squares regression line of this scatter plot up here. So this is the scatter plot of that up there. So they've worked it out. Now they've asked for the explanatory variable. Now remember, the x means on the x for explanatory, x for x-axis. So which is the explanatory? So you just write rainfall in millimeters, or whatever it is. Sorry, mine's very small. No, it is millimeters. Okay. Draw on the graph the least squares regression line. So what we want to do is we want to put this formula, this line, this is a straight line, onto this graph below. So I'll just write it out in terms of y. So we've got y equals 1164 minus 10 times rainfall. Okay, so essentially this bit is the y-intercept, which means when x equals 0. So if you have 0 down here on your graph, which we do, you can pop in this point. So it says 1164. So it's about there. So I'm just drawing it small. Now we need another dot. So I suggest that you pop in the last point into the formula. So what I'm going to do is 1164, minus 10 times 50. So 10 times 50 would be 500. So then this one would be 664. Okay, so when x is 50, y is 664. So I'm just going to say roughly there. Yours will be a little bit bigger on your paper. And then you simply get your 2 dots and you join them up. And they'll be looking for that. All right, so there you go. That's your line of draw the least squares line above on the graph plot, and grams per minute. Okay, just because I've gone over the page, I just wanted to put this information back up here, that they gave you the least squares regression line, and they also gave you the coefficient of determination. So when you see that, I often like to write r squared above it, just so I'm registering I've got the r square value there. So even could put it there. So write down the value of the correlation coefficient. So that is just r. So remember, we can find r by doing the square root of r squared, which is 0.5165. But we have to make a decision on whether it's plus or minus. So you would be looking at the graph, the previous. You can see that it's negative, so the r value is going to be negative. So you do the square root of that. Now we look for 2 decimal places. So I get negative 0.72. Okay, and there's my final answer. Most important thing is this check to see if it's negative or positive. Okay, in question D, it says interpret the vertical axis. So the vertical axis is actually the y-intercept, because that's the vertical line. okay, in terms of variables and salinity. So in your notes, you have a blurb. So you will be writing this down. You'd write the regression line intercept predicts the RV, which is the salinity, to be, and we put the value there, so the A value is that first one, to be 1164 units. So I've got to change the units, which was, I think salinity was milliliters. So I'll just write milligrams per litre, when the EV, which is the rainfall, is 0 millimeters. Okay, so you're putting the units of the EV there. In question F, it says interpret the slope in terms of the variables salinity and rainfall during the previous 24-hour period, 1 mark. So I've looked, it's a negative. So the salinity decreases by the B value, which is there, up there, -10. So you don't have to write negative because that's what the word decrease means. So it decreases by 10. Now you need to put the RV unit. So we write milligrams per litre, because that's what the salinity is, when the rainfall increases by 1, and you put the units of rainfall, which is millimetre. Okay? They're very easy marks. You've got the words, just copy it in. So the next question, what percentage of variation in salinity can be explained by the variation in thing? So hopefully this is triggering you that this is the R squared blurb. So they're asking you for R squared as a percentage. So we got it up there. Now just double check. They want 1 decimal place. So I got 0.5165 times 100. So it'll be 51.65. But they want 1 decimal place. So 51.7% of the variation is there. Okay, the residual plot for the least squares line is shown below. The residual value for the data point 21,720, which was shown on the scatter plot, was emitted from the plot above. So what they've actually given you this, they've given you the actual scenario. So what they've said when the rainfall was 21 millimeters, the salinity equaled 720. So this here is the actual. Now, when they've asked, they said draw in the missing residual value on the residual plot. So you need to write down your formula for residual. So residual on your notes is actual minus predicted. And you'll see, well, we've got the actual, we know it's 720, and we use the equation to get the predicted. So the equation was on the pages before, which was 1164 minus 10 times the rainfall, which we know at the moment is 21. So we pop that into the calculator. So we get 720 minus 954, which equals -234. So this is the residual for 21, the x point 21. So if you go on when rainfall, so I'm looking along here, when rainfall is 21, so somewhere around this line there, we're going to put the -234. So 234 would be up here. So we'll just pop in a dot up there and roughly. So you need to mark it. I don't know, maybe put a cross or whatever. This is a trial exam. They'll be a bit more clear on how to, I think they normally say cross it, mark it with a cross or something. Explain whether or not the residual plot supports the assumption that the relationship between rainfall and salinity and rainfall is linear. We're going to say yes, it does, and then we'll use this statement, which is in our summary sheet. So from the residual plot, we see that there is no clear pattern. So up here, the dots are just randomly scattered. So in the residual, so randomly scattered around the zero regression line. There's the zero regression line. And this confirms the assumption that it's linear. So you can write this whole little statement, which is on our our summary sheet. If you saw a pattern in the residual, you would say it does not it's not a really linear relationship. So there's the opposite. Just be careful. You can just make sure you write the opposite if it is. All right, further salinity testing of the river is conducted. The table below shows the salinity of the river measured at the end of each month during 2019. Describe the trend shown in the time series plot. So I would say that overall it's just a general upward trend. Can't see any really. So I would just say a general upward trend with maybe random variation. Okay, it says use the data in the table above to determine the equation of the least squares regression line. Write the values of the intercept, which is the A value, and the slope, which is the B value in the boxes below. Now, very important, round your answers to 3 significant figures. So if you have a look, I've put the list in, so I've got months into there, and then we've got popped in the salinity. So months is going to be your X, and salinity will be your Y. And we've popped them in, and we've got our answers. Now, if you look here, we've got the A value. Now, they want us to 3 significant figures. So you start counting as soon as you have a non-zero. So 1, 2, 3. So they're the 3 significant figures. I look at the 4th one to see if I have to round up the 3rd one. And I don't, because it's a 3. So my A value is 279. And then I go and look at the B one down here. And we're going to start counting. So 1, 2, 3, and you look at the 4th one to see if it needs to go up, and it doesn't, so it's 76.5. So there's my 3 significant figures. Okay, an associated study measured the salinity of 9 creeks that flow into a river together with the length in kilometres. The data is collected and shown in the plot and table below. So just take note, this is different data now. Okay, so we've got different. What is the median salinity in milligrams of the 9 creeks? So there's a couple of ways you could do it. You could go and type this list into your calculator and ask for the median and calculate the median using the stats. That could take a while, because the other way you could do it is that you could say, well, if you've got 9 creeks, n equals 9, so the median is found at the n plus 1 divided by 2. So 9 plus 1 divided by 2. So it's the 5th highest, or 5th, the 5th, value when you're going lowest to highest. Okay, so 5th from lowest to highest. So all you can do is you can move up the salinity starting at the bottom and till you get to the 5th highest one. So obviously this is the lowest, 1, 2, 3, then this one, 4, and this guy is 5. So if you measure off here, this is at a length of whatever, the 2.6 here. So it is the 114. So I can go round and I can see on the table. So I just found out. And so then I can say the median is 1140. You'd get the same if you did it in the calculator. I just think this would have been quicker way to work it out, because they have put them in, you can see on a graph, smallest to largest. So, what is it, 1.8 to 8.8. All right, the association, between the salinity and the length of the creeks is non-linear. Yeah, we can see that there was a curve. A square transformation can be applied to the salinity. So they're doing a y squared transformation. And the least squares line can be fitted to the transform data to attempt to predict the salinity squared. So, yep, of the creek from its length. The name of the response variable for the transform data, so response means y, so this one will be salinity squared is the name of the transform data. Okay, so now it says determine the intercept, which is the a, and the slope, and they've said to the nearest whole number. So what I've done is I've entered in the two lists, length and salinity, and then I've created the squared list. So then once we've done the squared list, we do the linear regression, the a plus bx, and just remember that the x list is still length, but the y list you need to pick your salinity squared, okay, which is what I've done over here. And now I've got my a value and my b value. Now they said to the nearest whole number, so that just means before the decimal point. So here is the whole number there, so I'm going to write that out. So it's 2, 8, 2, 6, 2. Now the last 6 I just checked at 0, so it doesn't get rounded up. And this one to the nearest whole number, but that's a 9, so I will have to round that one up. So the B is 201,383. Okay. The least square line predicts the salinity of the creek with a length of 15 kilometres. So they're giving you a salinity squared when the length is 15 to be this. Calculate the expected salinity of that creek, 15 kilometres, using this information. So if they've given you salinity squared, you can find the salinity by square rooting this salinity squared. So what we're going to do is we're going to do the square root of 330371 and find out the salinity of that. Okay, so we end up with, now it said to the nearest milligram, so we end up with 1818 milligrams per litre. Okay, so that one you have to use the data they gave you, so don't be tricked in going in trying to find or using something else, just use that data that they just said there. Explain why the predicted salinity level found in part B part I may not be reliable. Now if you are predicting, they said they predicted using 15 kilometres. Now our range for length is actually we range from 2, what's our low? Okay, so our lowest length, river length, was 1.8 and the highest one was 8.8. If we predicted within there, it's interpolation. If we predict outside, which 15, it's extrapolation, so it's unreliable. So you just write, is it reliable? It's not reliable, as it is extrapolation, sorry, hopefully you can spell, which is, sorry, remove all this on, which is testing or predicting, or might say, which is predicting outside the range. Outside the range. Okay. And then there you go. The time series plot below shows the monthly rainfall in millimetres that fell in the area where the rivers flows during the months in 2019, January to December, months 1 to 12. Determine the 5 median smoothing rainfall for July 2019. So really what they're doing, the 5 median month for July in 2019. So we want, when we do median, we do it on the graph, which makes sense because they've given us the graph. Remember, July is the 7th month, so there's the 7th. And if we're doing 5, we want 5 dots. So we want probably 2 below it and 2 after it. Now what I'm doing now is using my ruler, and I'm moving from the bottom up to the top. Now if you have 5 median smoothing, it will occur on the 3rd. So if I go through, this one was, this guy's 1, then I hit that one, which is 2, so 1, 2. Now you can see here is, this guy's the 3rd. So whatever this value is down over here, which looks like, what are they, is it going up into 32, 4, 6, 8, so 38. So we're going to say that it's 38 millimetres. Oops, 38 millimetres, and that's how you do that. Okay, the seasonal indices for the monthly rainfall in the area are shown in the table below. For the entry for June is missing. The monthly rainfall that fell in the area of June was 42. Find the deseasonalised value for the monthly rainfall in June 2000. Round to the nearest whole number and 1 mark. So what you want to do, you get the formula for deseasonalised, and you can see that deseasonalised is actual over seasonal index. So they told you the monthly rainfall fell in the area was 42. So right there, they gave you the actual. So you know the actual. So deseasonalised is actual, which will be 42. And we need to divide by the seasonal index, which is missing. So all these seasonal index should add up to the total amount of seasons. So when you have the months of the year, they should all add up to 12. So if you're going to find June, it would be 12 minus all the others added up. Okay, so when you do that, so 12 minus all the others, which end up being 11.3. So June's seasonal index ends up being 12 minus all the others, which was 11.13, which ends up 0.87. So 0.87. So now I can divide by 0.87, and I do this, and it said to the nearest whole number, so it ends up being 48. All right, so next question, what does the seasonal index of 1.10 about the monthly, tell us about the monthly rainfall? So when it's over 1, it's telling us about, so it tells us that July is 10% above average. So you can change that to a percentage, the 10% above average.